So good afternoon, everyone. I'm Stefano Forti. I'm a postdoc researcher at the Department of Computer Science of the University of Pisa and the Service-Oriented Cloud and Fog Computing Research Group, which is led by Antonio Brogi. And in the next few minutes, I'll try to give you an idea of what we are working on in the context of VNF chains, placement in fog computing infrastructures. So we all see this never-ending increase of IoT applications and of the data they produce all around us being embedded in our lives. And on the other hand, we also see an evolution of the software architectures that will support this shift or this increase of data being produced by the IoT. And so we have multi-component, osmotic, microservice-based architectures, but also virtual network function chains that can be deployed on commodity hardware, virtual machines, or containers throughout the network to support computation at a multi-level at multiple levels. And similarly, the infrastructure is changing to support this trend, and so now we have a computing continuum that spans pervasively from the IoT to the cloud. The infrastructure with computing capabilities, with storage capabilities, as Monica was mentioning before. And all these applications, they have stringent quality of service requirements, such as they must comply with very low latency, with suitable bandwidth availability, with cost. And so guaranteeing all these on top of an infrastructure that can change, that is very dynamic, might be difficult, and it's an interesting problem to study. And so the questions we have tried to answer is how can we deploy basically these complex, large, highly distributed software systems on top of pervasively distributed infrastructures, so to guarantee all their stringent quality of service requirements. The problem is known to be NP hard, so we must keep calm, and we have found two research questions to follow. So the first one is where to deploy virtual network functions to fog infrastructures, so to satisfy the hardware requirements they have, and the IoT requirements they have, and the security requirements they have. And the second one is how can we route the traffic flows between virtual network functions by suitably instructing the SDN controller that routes traffic between them. And so our proposal is this methodology and open source prototype, which is called EdgeUsher. You can find it on GitHub, and there's a technical report on Archive. And basically, EdgeUsher is a probabilistic declarative prototype which solves the VNF placement in a fog scenario according to the declarative approach. It basically inputs a probabilistic infrastructure. So we make the hardware bandwidth and latency in the infrastructure vary, which is also annotated with security capabilities that nodes can feature. And also these security capabilities might be subject to changes. And then we have a VNF chain that has the requirements that can be matched with the infrastructure capabilities, so hardware, software, network QoS, and security requirements. And the output of EdgeUsher is a ranking of the eligible VNF placements and the routing paths based on how likely they are to comply to all the application requirements, to all the VNF chain requirements. Now we have a look at one example. This is a real topology that is deployed at UC Davis. And we have like 10 nodes at the edge, plus we can't see the picture, but there's an ISP provider, fog node, and the cloud virtual machine that extend this network, this infrastructure. And here, just as an example, we have different kinds of links, and they have a probabilistic behavior. So the edge-to-edge links that we see here, the dashed ones, they have 98% of probability of featuring 70 megabit per second and 15 millisecond latency, but 2% of the times they're unavailable. And we have probabilistic profiles for all the other links in the infrastructure. And similarly for the nodes, we have that, for instance, the small one, these ones which are yellow and annotated with a 2, they feature full capacity to 2 hardware resources in 20% of the cases, but 80% of the cases, they only feature one hardware capacity. We use generic hardware units for the sake of simplicity. Of course, this can be extended to have profiles with RAM, hard disk, and virtual CPUs or physical CPUs. And then they feature also security capabilities, which are different depending on the node type. On the other hand, we can see this example VNF chain that has is made of a series of virtual network functions, and each virtual network function has hardware, security, and processing time requirements, and it also has connections. It connects to possibly other VNFs in the chain by declaring the amount of bandwidth, the minimum amount of bandwidth that is needed to support function-to-function communication. And finally, we have this blue dotted line that indicates the end-to-end latency that must be present between this CCTV system driver that detects anomalous behaviors or fire at the car park and immediately alerts the police station or the fire station to intervene. We have IoT devices here and here. So now we see also a small prototype implementation of, just to give you a dash of what declarative means. Here we have a clause, a Prolog clause, because the prototype is written in Prolog, that says that we can place a function identified by FID onto a node identified by NID if basically the function ID identifies a service with certain hardware requirements, the node ID identifies a node with certain hardware capabilities, and then the hardware requirements are supported by the capabilities of the node. And so here we see that the capabilities of the node must be greater than or equal than the required hardware. Then we can have a service which has an instance of a service which has an ID and some hardware requirements, and a couple of nodes. One called Student Center that has 8 hardware capabilities, and the other one, Brigzol, which only has 2. And then we can query our prototype, our small prototype. This is just a toy example of what EdgeUsher is. And we obtain that, yes, there exists a node that supports our service, and this node is the Student Center node. As a second step, now we have the check on the hardware, we can add a check on the IoT. So basically, we will add another clause here to check IoT capabilities that are now available at the node, are in the node descriptor, and they're available as requirements in the service descriptor. And we basically look if all required things are available at the node. And again, on the small example, we check if a node can support our requirement. And we have, yes, the feature extraction that analyzes video stream from the car park can be actually deployed in between these two nodes at the parking services, because the parking services node features the required video camera. And finally, which is a point of novelty of our approach, we also have a way to specify security policies for the deployment of applications. And these security policies can be empty. So in the case they're empty, we have nothing to verify, they're okay. They can be a list of required security policies. So for instance, we want anti-tampering capabilities or encrypted storage available at the node where we will deploy our application, our VNF. Or they can be compositions of policies obtained via an AND clause or via an OR clause. Or they can simply be one atom. So basically with this, we define a small language that can AND or security capabilities, so to define policies for each and every VNF that we want to deploy on a target infrastructure. And similarly to before, we now have this extended representation of a service with the identifier, the hardware capabilities that it requires, the IoT devices that it requires, and an OR clause with other anti-tampering or access control to the target deployment node, and we can match it with the description of available nodes in the infrastructure. And also in this case, yes, we can deploy our function on the parking service node that features that features the anti-tampering capabilities. So this just to give you a dash of what the prototype looks like. And basically then the full EdgeUsher has been extended to place chained functions. So not only a single function on a single node, and also to check cumulative other requirements. So to be able to map more than one function on the same node. It has been extended to determine routing of traffic flows in between nodes, so to enforce latency and also cumulative hardware bandwidth requirements. So again, communications, more than one communication between couples of functions can be mapped onto the same point-to-point links. And then it also exploits probabilistic input, as we have seen before, by relying on the problog extension of Prolog, which is what helps us in assessing how likely a placement is to meet all the requirements of a chain, and then to rank the output placement that we get. Full EdgeUsher also allows to easily expressing affinity or anti-affinity constraints, so to impose that two functions are placed or not onto the same node. And also partial placements. So if I'm sure that some functions are already deployed, or I'm not interested in moving them from their from the node on top of which they're currently deployed, I can also specify partial placements and then try to place what is not placed yet. Here we see the example solved, basically the example we have seen before. And here we have basically that all the different functions have been placed, have been spread on the fog infrastructure that we have here. And we also have the routing of traffic flows among the different nodes with the cumulative bandwidth that they occupy on the end-to-end links. And this is actually one of the best deployments because taking into account all the changes that can be that can happen in the substrate infrastructure, it still features a requirement satisfaction probability of 98%. Now assume that we want to deploy a second chain, part of which we will exploit. So we want to only redeploy the dashed services that we had here. And now in this case, we get two possible equally optimal results that satisfy the requirements with a 96% probability. Now it will be a duty of the application deployer, be it autonomic or human, to decide whether this is a sufficient probability to deploy the CCTV system and to suitably support the application that the VNF chain enables. Now about performance, EdgeUsher, of course, in its basic version is exp time because it solves an NP-hard problem. So in the worst case, it has to explore the full search space, which is combinatorially exponential. And so this is the performance of the exhaustive search. Of course, this is not very good because if we don't have probabilities, it only takes 8 seconds. If we only use one probability per each link, it still takes 8 seconds. But then when we want to use the full probability distribution, it takes almost 3 hours to run, which is really unfeasible if we want to make quick decision making. And so we also have a heuristic version that allows to specify a threshold for the probability. And so to prune the search, as soon as the probability of a deployment meeting all the requirements falls below the threshold. And in this case, we see that in less than 1 minute, we get 6 of the best placements that we also got in the complete search space with the exhaustive search. So basically, the heuristic algorithm prunes on the probability of satisfying all constraints, and the determined placement, the determined embeddings are in the Pareto optimal front of the solutions that are possible for this problem. To conclude, EdgeUsher permits solving the VNF placement problem in a declarative manner, both via a exhaustive search and heuristic strategies. And being declarative, it is quite concise. So with respect to procedural solutions, which are around 1,000 lines of code, EdgeUsher is only 72 single lines of code. It is quite flexible and extensible. So as you're seeing, it is easy to write it, and it can support other different taxonomies for the security capabilities, as well as new requirements as soon as they will be established in fog scenarios. And since it relies on state-of-the-art resolution mechanisms in Prolog, it is explainable. And it can also be, it's also possible to get a graphical pictorial explanation of why a certain deployment can be considered valid and secure. Finally, it determines resilient placements. So since it doesn't look to the static current state of the infrastructure, but to historically monitored data as well, it is more likely to ensure QS guarantees security and service reliabilities when the infrastructure varies, so when a node fails or a link fails. And as future work, we have three main directions. So one is the tuning of the heuristic thresholds via learning, so to adapt to different application scenario. Then we're currently working to have a graphical user interface which permits application developers to define their chain and visualize the placement of the chains on top of a graph that represents the infrastructure. And finally, we are currently working at a testbed for fog computing at the Department of Computer Science. So we're going to assess EdgeUsher both on the real testbed and in simulated settings by taking monitoring data from the actual testbed that we will build. And this basically concludes my talk. So I'm ready to take questions, if any, and I thank you for your attention.
Yes, thanks a lot, Stefano, for the very nice talk. Again, as I said before, feel free to send questions through the Q&A or raising your virtual hands. Virtual hand one is enough in Zoom. So, well, I have a question. So, if I got it correctly, it's quite easy to describe, let's say, the deployment model using your application, right? But
yes.
I was wondering how easy it is to get this infrastructure. So the information that you retrieve from from the actual deployment, because for a fog environment, everything is very, very dynamical. A lot of nodes can change. From your infrastructure, you can add nodes, not even remove nodes because there are some faults, but you can even dynamically add nodes. So I was wondering, I know that this is part of your future work, but I know if I want to ask you if you have an idea about this.
Yeah, actually, currently we have a prototype monitoring tool that can retrieve data and also actually aggregate it, probabilistic. It's called FogMon. And it's also open sourced, and adapting it to, let's say, input data in the EdgeUsher format is quite straightforward because it already aggregates the probability distributions. So, I mean, it's just a matter of pipelining them in a good manner. And for what concerns variations in the infrastructure, basically FogMon has a peer-to-peer architecture. So that it is resilient to faults, and it's able to self-reorganize in case, like, it's organized as a peer-to-peer leader-follower architecture. So in case a leader or a follower crashes, we have self-healing mechanisms that reorganize the overlay, so to keep monitoring up and running.
Okay, that's very interesting. Thanks a lot.
Thank you.
So is there any other question?
I have a question.
Please.
You were discussing the fact that you're actually modeling a chain of functions, right? So you are trying to also catch the dependency between them in terms of, let's say, the workflow between the different functions. My question is, how can you actually manage this chain. So it's only a matter of how the process is designed in terms of you have a previous knowledge of the sequence of functions. So you just consider this information, how many variations you can have, because maybe this set of functions is dynamic. It depends on the data that you have, the context in which you are executing your application. And also, if you are considering the dependency in terms of data that these tasks, these functions are using, that might in some way change your decision about the deployment. Because if you have to move an enormous amount of data between two different functions, then maybe it's better to deploy them together, or otherwise you can take different decisions. So I wanted to know what aspects you are considering in this workflow.
Right, thanks. The question is very interesting, and actually it's like 3 questions in one. So each question is a good hint for future development of this work. Currently, we take the description of the service chain as it is. So the functions are just black box, annotated with their requirements. But definitely, it would be very interesting, especially from a security perspective, to have some more contextual awareness, and so to decide, for instance, that if I need a firewall, I can actually run it in run a software, a function, an extra function that I don't have in my chain to have the firewall deployed on my node. And so this is a line for future work. Instead, data flow, for now, we are abstracting from it, but it's definitely a very interesting point to look at, because it also allows to do more fine-grained security analysis, like with information flow security, and that's very interesting. So thanks for the question hint. I don't know if there was a last point, if I answered to all your question.
Yes, thank you.
Thank you. Okay, so thanks a lot, Stefano. I think we can close here this part here and move to the next talk, which is the title Secure Lifecycle Assessment in Complex Supply Chains. So Sakin, the virtual floor is yours.